All right, today we're going to look at electron configurations and then add what's called orbital notation. So the first time I did the quantum note sheet, I skipped some things intentionally. So I'm going to go back and kind of refill these. So wave-particle duality. So waves, particles, and duality kind of puts together is particles can act like waves, and waves can act like particles. Okay, and you already saw this idea. Photons is the particle nature of light, where light sort of bundles together and kind of works as a unit. So that's the particle nature of light. So what this means for the wave mechanical or the quantum view of an atom is that electrons are moving so fast that the exact location can't be known. So all of these orbitals that you looked at in the original note sheet are all probabilities of where electrons will be, but electrons really can be in any place at any time. But these zones that we mapped out on that crazy diagram are the most likely places for them to be. Okay. So electrons act as waves and occupy a region rather than a single point. Okay. And then the other thing you need to realize is that all of these are numbers. So that n is the one we've seen the most. 1 to 7, these are your period numbers. So when we say 1s2, we're talking about n is 1. When we're talking about 5p6, we're talking about n equals 5. This shape probability, so the SPDF, has a number notation that goes with it. So there are mathematical equations that create all of these shapes. So we're not going to get into that, but it does go over that. So today's focus is going to be looking at these two ideas, that orientation of the orbital in space and the direction of the spin. So you'll notice that these are opposite. So we're going to do an up arrow to represent a plus 1/2 and a down arrow to do a minus 1/2. So this is important. Each electron is unique. So no two electrons in the same atom have exactly the same set of quantum numbers. So even the two that are in the 1s are going to be slightly different. And this is known as Pauli exclusion principle. So you saw that kind of with the sunny and pink rooms in that first electron configuration. So I'm going to start by doing orbital notation, kind of giving you a little bit of some things that we've already done. Okay. So on this back path we did, or back page of this, we did these original electron configuration. So to add orbital notation, we're going to actually just label and show the arrows. So for hydrogen, this would be 1s1. Different books do this differently, so you might see a block or a box with this. Some use circles. Again, it's just easier to do the dashes. So each line represents an orbital. So all of these would be ways to explain the hydrogen. Okay. Now, I'm going to sneak down to nitrogen. So for nitrogen, we have the 1s. So again, if you look at your periodic table, you can tell how many lines to draw by how wide this is. So if we look at our P block and our S block, okay, it is 2 elements wide, so 2 divided by 2 gives me my 1 block, because the first electron for nitrogen is going to be, line that up very well, 1 up and 1 down, because one's going to be spinning clockwise, one's going to be spinning counterclockwise. When we go to the 2s, again, I'm still going to have 1 orbital because there's only 1 location where that's going to be. Okay, and its 2 electrons are going to go here. When I get to the p block, I'm going to have 3 orbitals. So again, if we go back to our notes on the other side, okay, there is a px, a py, and a pz, and we are basically going to distinguish which one of those it is by giving each one of them an individual line. Okay, and you might remember in that room analogy, we don't make anyone share a room until we absolutely have to. So those 3 electrons are each going to occupy their own orbital. Okay, now when we get to fluorine, let me change color maybe. So this is nitrogen. Okay, so once I get to fluorine, I'm still going to have the 1s with its 2 electrons. I'm still going to have the 2s with its 2 electrons. And then my 2p, okay, and we could label these px, py, pz. That's what they really represent. I'm going to put the first 3 in up, and that's really arbitrary, but they're all in the same, or they're parallel. And then I have 5. So this is like when your parents run out of bedrooms in their house. If they have more kids, they start making you share rooms. So kid 4 and 5, or electron 4 and 5, have to share a room. So that's what its orbital notation would look like. Okay. If we jump to the D block and look back at our periodic table for the D block, so again, if you count the rows, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, there's 10 electrons in this row. So I need to divide that by 2 because each electron, or each orbital, can have 2 electrons in it. So 10 divided by 2 is going to give me 5. So I am going to do iron. So this is going to be iron. So I'm going to do 1s, 2s, 2p, 3s, 3p. So notice I'm just in the habit always do up, down, even though these are filled. 3p, 4s, and then my 5 for the D. So I'll have 5 lines, 1 for each of those orbitals. 1, 2, 3, 4, 5, and then the 6th one has to pair up and share. Okay, now you can see this gets pretty tedious as well, so we can do short form for this one as well. So if we do short form for molybdenum, so remember all of this for molybdenum is going to be argon, so I could say that's argon, and then just 5s2, 4d10, or excuse me, 44. So for molybdenum, I'm going to have 5s if I do short form. I still have 5 orbitals in the 4d. Now what you'll notice is I don't have them all filled. So this is a big house and we have some empty rooms that aren't used yet. Or the analogy could be when you're at school, your room still exists, you just don't happen to be in it. So this configuration, you still show all of the orbitals even if they're not all filled. And the same can filter through for the f orbitals as well. Okay. So if I come down here to bismuth, so again, referring back to my periodic table, so remember the 14 here are the F. These 2 belong up here in the D. So 14 divided by 2 is 7. So for bismuth, I would do my for bismuth, I would do my 6s with its up-down arrow. The 7, So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So that's my 4F. 1, 2, 3, 4, 5 for my 4D, excuse me, 5D. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then my 6p, 1, 2, 3, and I would just have 3 electrons. So even that's still pretty long, but it's again showing us where those electrons are. If I do uranium, that one's a little shorter. I'd have my 7s. 1, 2, 3, 4, 5, 6, 7 for the 5F, but again, they are not all full, so just those first 4. But again, these empty rooms still exist. Those locations in the atom are still there, even if there aren't any electrons in it. Okay. All right, this is going to lead us into bonding. So I have a practice sheet for you, and so the first one's been done for you. So the electron configuration and orbital notation, this has a little more space than this last worksheet. I am going to sneak down to germanium. As an example I'm going to do with you. So this is element 32. So okay, I'm going to do short form. I think if you don't have to do long form, this helps see this. Just argon, what we need is really here. So argon is what we're starting with, and then we're going to do, and again, if you number these, I know not all of my copies give you a lot of room for that, but this would be 4s2, 3d10, 4p2. So I'm going to do that short form for germanium. Okay. And then I'm going to do my 4s, my 3d, and you could draw the up-down together. It doesn't really matter, but I just always do the habit of all the up ones first. And then my 3 orbitals for the 4p and 2. So for bonding, what's going to become important is how many shared and unshared electrons you have. So you'll see in magnesium, everything is shared up, so there's no unpaired. But for germanium, we would have 2 unshared electrons. So again, we are heading toward the bonding unit, so this is all going to be important as we move forward into that bonding unit. Okay, so that's an example for that side of the worksheet. Okay, and notice they knew the noble gas shortcut over here for the orbital notation, so that's just doing the lines. And they asked for the number of electrons, so there's 82 in lead. We're not going to draw all 82. Okay, so for lead, we're going to go back to xenon. So that's 54. 55 takes us here, so 6s2, remember 56 takes me down here, or 57 brings me down here, 4f14, 71 to 72 brings me back up here in the D block, so 5d10 and then 6p2. All right, I am vastly running out of recording time here for the app I'm using. So this is the completed one for here. So there would be 2 unpaired electrons. So the next part C is going to talk to you about rules and explanations. So Hund's rule is this idea that we have to put 1 electron in each orbital before we pair up. Pauli exclusion principle has been discussed, and the Aufbau principle is